So today we're going to be looking at how to solve an exponential or logarithmic equation. So we're going to need our logarithms from the last lesson to be able to do these. And then we're going to be able to use these to help us solve word problems next time. Before we start, we're going to make this little table. It's tedious, but it'll come in handy as you continue through this section. It's just going to be a list of powers. So you can use this table to help you with questions from your section. A calculator obviously would work as well, but sometimes people sit there and go, okay, 2 to the power of 3. Nope, that's not it. 2 to the power of 4. Oh, that's not it. This would just be, you can quickly look at it and see, obviously, not every power in the world is on here, but kind of the most common ones you might come across should be on this list, except for maybe powers of 10. But hopefully this will be helpful as you go through your homework. So when I say powers of, I mean things like 2 to the power of 2 is equal to 4. 2 to the power of 3 is equal to 8. 2 to the power of 4 is 16. The power of 5 would be 32. And then we'd have 64, 128, and 256. So these are the bases, and these are the exponents. Okay, we're just going to fill this in. 3 squared would be 9, 3 cubed, 27, 3 to the power of 4 is 81. Then we have 243, 729, 2,187, 6,581. Okay, 4 squared, 16, you've got 64, 256, 1,024, 4,096, 16,384, 65,536. We have 5 squared, 25, 125, 625, 3,125, 15,625, 78,125, 390,625. So again, I mean, you would not be expected to memorize all these. You have a calculator. It'll figure them out. It's just, we're hoping to save you a little time down the road here. 6 squared, 36, 216, 1,296, 7,776, 46,656, 279,936, and the last one, 6 to the power of 8, give us 1,679,616. Okay. So we're going to use these to help us solve some equations. Okay. 3 to what power gives me 243? If I look at my chart, 3 to the power of 5 gives me 243. Okay, so how I would write this down, obviously I can just look at my chart and see that my exponent is 5. But for later on, I'm going to write down that this would be 3 to the power of x equals 243. If I rewrite this, I get 3 to the power of x equals 3 to the power of 5, and therefore x equals 5. Obviously, for these couple questions, this seems super tedious, and why would we do this? But you're going to see when we start solving questions later on where it's not so obvious why. Okay, next one. So I've got 4 to the power of x is 1 over 256. So this is the same thing as saying 4 to the power of x is the same thing as 1 over 4 to the power of 4, because if I look at my chart, I have here 4 to the power of 4 is 256. And if I rewrite this, this is the same thing as 4 to the power of negative 4, which means that x is negative 4. Okay. Now, when we look at the next one, we see that we don't have the same basis. This is not obvious. So before we start, we must make the same basis first. So 27 and 9 can both be written as a base with 3. So 27 could be rewritten as 3 cubed. So instead of being 27 to the power of x, I could have 3 cubed to the power of x. And on the other side, we have 9 to the 2x minus 1. Instead of a 9, I could rewrite this as 3 squared to the 2x minus 1. So the 27 has been replaced with a 3 cubed, and the 9 has been replaced with a 3 squared. If I'm using my chart, what I'm really doing is I'm looking for what row do I have 9 and 27 in. So this is the base I can use. I can use a base of 3 to rewrite both these numbers. Once I've done that, I need to use my rules from grade 9 and 10. Once I have the same bases, I can rewrite this as 3 to the 3x equals 3 to the 4x minus 2. Because if I have the power of a power, my exponents multiply. So 3 times x gives me 3x. 2 times 2x minus 1 would give me 4x minus 2. And that means that if I have the same base, my exponents must be equal. Okay, so this must mean that 3x equals 4x minus 2. The same way here my exponents were equal, and the same way here my exponents were equal. The same thing happens. Yes, I don't have just an x on one side, but my exponents still must be equal. Once I have that, I can solve this. I get 0 equals x minus 2, so x is equal to 2. Okay. So again, just a quick review from radicals in Math 10. We did a fairly tedious way of rewriting these last day. If I have some number inside of a radical, the index of that radical, which in this case is our a, becomes the denominator of a fractional exponent, and the power on the x becomes the numerator of the fractional exponent. We also have some radical rules that if after last day you still don't have kind of remembered, we have x to the m to another power n, a power to a power. We multiply the exponents. Okay. If we have two powers that are multiplying with each other, we can add the exponents. And if we had two powers dividing by each other, we could subtract the exponents. So an example, 2 cubed to the power of 4 is 2 to the 12. 2 cubed times 2 to the 4 would be 2 to the 7. And 2 to the 4 over 2 cubed would be 2 to the 1, because 4 minus 3 is 1. Okay. So let's try some questions. We're going to use these rules to try and solve these equations. Step 1 is always try and make the bases the same. As soon as the bases are the same, the exponents must be equal. Okay, which we saw before, right? All those questions we just did on the previous page, our bases were the same and our exponents were equal. We're doing the same thing here, it's just a little bit more simplifying, okay? So I can tell by looking at this first question, I've got 2 to the power of x on the left. There's nothing I can do to simplify that. There's nothing I can rewrite, so my base must be 2. On the right, I can see that I've got a cubed root of 2, which I can rewrite as an exponent, and I've got an 8, which I can rewrite with a base of 2. So I'm going to keep the left the same. I'm going to rewrite the 8 as 2 cubed, And I'm going to rewrite the cubed root of 2 as 2 to the 1/3. Okay? I haven't changed any values. I've just rewritten the 8 and the cubed root 2. Now I can use my radical rules that I just wrote down. I've got 2 powers with the same base. That means I can rewrite this as a single power with that base. And I know that that means my exponents are adding together. Okay? If I add these exponents together, I'm going to get 3 plus 1/3. You'd need common denominators for this. This would be 9/3 plus 1/3, or 2 to the 10/3. And the left side this whole time is staying the same. Well, now we can see this means x is equal to 10/3. Okay. All right, now this next one's not quite so obvious because neither of them are written as some base to the power of x like the previous one. So what again I need to do is say, well, what base could I use on both sides? So if I take a look at my chart from page 1, I would see that 125 and 625 can both be written as a base of 5. So 125 is 5 cubed. So I'm going to rewrite the 125 as a 5 cubed. 625 is 5 to the power of 4. Okay, so the first thing I'm doing is changing the 125 and 625 to have the same base as each other. Once I've done that, I would choose to next deal with the radicals. I'm going to rewrite the radicals as fractional exponents. So on the left, I have a square root, which is going to mean this is 5 to the 3/2 to the 2x plus 1. And on the right-hand side, I have a cubed root, so this is going to be 4/3. Now again, my bases are the same, which means my exponents will need to be equal now. And on the left, I have the power of a power, which means my exponent on the left is actually 5 to the power of 3/2 times 2x plus 1. You're welcome to expand that here if you'd like. So if you want to go straight to expanding it, you would have 5, 3/2 times 2x, 1.5 times 2, which give us 3x plus 3/2 equals 5 to the 4/3. So once we have that, our exponents must be equal. So if you were doing the left version where you didn't expand it yet, you would have 3/2 times 2x plus 1 equals 4/3. I'll rewrite that. You were doing the right version, you'd already be at 3x plus 3/2 equals 4/3. And then we need to solve for x. So on the left side, we can multiply by 2/3, or we can expand this out. If we expand this out, we get 3x plus 3/2 equals 4/3. And then we're on the same spot on both sides here. So let's just solve these together. So we are going to get 3x equals 4/3 minus 3/2. We need to figure out what 4/3 minus 3/2 is. We need common denominators, so our denominator would be 6. So we get negative 1/6. Okay, so we actually have 3x equals negative 1/6. Now if I divide both sides by 3, I get x equals negative 1/18. So there's no way we would have been able to guess and check this. Okay, so step 1, make the bases the same if possible. Okay. Step 2, try and rewrite any radicals. And then once you have the same bases, the exponents must be equal. Now, we can't always make the bases the same, okay? And so then we would use logarithms to do those questions. And we're going to do some of those in a little bit. Before we can do that type, we need to be able to solve a logarithmic equation. Okay, so if we had an exponential equation where we can't make the bases the same, we need logarithms, but it turns it into a logarithmic equation. So we need to solve a logarithmic equation first. So the first thing I'm going to do is use log laws to combine this so that I can rewrite it in exponential form. Okay, so to solve a logarithmic equation, my first thing I'm going to do is rewrite as a single logarithm. Whoops. Using log laws. Once I've done that, I can then rewrite it in exponential form so that I can solve it. Okay. So this one here, we can see that we have a plus in between the two logs, which means we can use our product log law from last day. They have the same bases and we're adding. So this is going to be rewritten as log base 3 of 9x times x equals 4. Now, if I rewrite this, I can rewrite this and simplify a little bit first and rewrite this as 9x squared. Now, reminder to rewrite in exponential form. Remember that if you have log base a of b equals c, this is the same as a to the power of c equals b. So here, our a value is 3, our c value is 4, and our b value is 9x squared. Now we can solve this. 3 to the power of 4 is 81. Okay. And if I solve this, divide both sides by 9, I get 9 is x squared, which means plus or minus 3 is x. Now, if you remember, there was a little tiny piece of information last day that said the inside stuff of our logarithm can't be negative. So we can't log a negative number. So we can't put negative 3 in here or in here. It won't work. Okay. So we can't log a negative number. So we have x equals 3. That doesn't mean when we solve these equations, we can't get a negative answer. You need to take a look back at the original question and see if your number would work. Okay, and I'll show you a couple examples of this later on. But for example, if I had, let's say my original question was log base 3 of 9 plus x, x here could be negative 3, because when I plug that in, I'd actually get log base 3 of 6, which is allowed. So you don't just automatically discard any negative answers. You do need to take a look back at the original question and see, would that result in me logging a negative number or not? In this case, my negative answer would mean I'm logging a negative number, which is not possible. So we're going to try another one here. Again, step 1, I'm going to rewrite using my log laws. So I've got plus, so this is going to be rewritten as log base 3 of x minus 4 times x. This is all inside our log, equals log base 3 of 21. Now we have a problem here. We can't rewrite this in exponential form because I don't have log base 3 of all this stuff equals an actual number. And log base 3 of 21 is not something easy I can do. But I do know that these bases are the same. There's nothing else going on. The inside stuff on each side must be equal. We think about this logically. Log base 3 of something equals log base 3 of 21. That something must equal 21, right? So I can say x minus 4 times x has to equal 21. And now I can solve this. I'm going to expand my brackets. I can see I've got a quadratic, so I need to make this equal to 0. and then I need to factor. If I factor this, I get x minus 7 and x plus 3. So x is equal to 7 or negative 3. So if I take a look back at my original question, I've got log base 3 of x minus 4, and I've got log base 3 of x. So if I put in here a 7, 7 minus 4, that will work. If I put in here a negative 3, I get negative 3 minus 4. That's not possible. So I can't use the negative 3. I can only use the 7. And if I take a look at this one, same thing. If I put 7 here, I have log base 3 of 7. That's fine. But if I put a negative 3 in here, I've got log base 3 of negative 3, and that's no. If you try that in your calculator, it'll say. All right. So let's try one more that kind of combines this quadratic idea, but also rewriting as exponential form. So step 1, rewrite using log laws. So I've got log base 2, got x plus 3 times x plus 5 because of the plus inside the two logs. And this is all inside our logarithm. Now I can rewrite this in exponential form because it just equals a number here. There we go. Oh, no, we're still thinking. Just gonna wait for my, oh, there we go. All right. So again, if I've got log base a of b equals c, this is equivalent to a to the power of c equals b. So this time I actually equal a number c I can rewrite. So my a would be 2, my c is 3, and my b is all this inside stuff. 2 to the power of 3 is 8. On the right, I expand, I'm going to get a quadratic, so I'm going to do that. I get x squared plus 8x plus 15. Again, once you have a quadratic, we know we need to make it equal to 0 and factor. So I'm going to subtract that 8 from both sides. And then if I factor, I get x plus 1, x plus 7. So x is equal to negative 1 or negative 7. So see what I mean? We've got two negative answers. That doesn't mean they're both automatically rejected. We need to take a look at our original question. We had log base 2 of x plus 3, and we had log base 2 of x plus 5. If I plug negative 1 in here, I get log base 2 of negative 1 plus 3. That's okay because that ends up being log base 2 of 2. If I plug negative 7 in here, I get log base 2 of negative 7 plus 3. And this does not work because I end up with log base 2 of negative 4, which is not okay. So I have to reject the negative 7. I would also want to then, I've already rejected negative 7. I don't need to test it in the other log. It's fine. But I should double check that my negative 1 works, and it does. I'd get log base 2 of negative 1 plus 5, which gives me log base 2 of 4. I'm not actually asked to figure out what those are. I literally just want to know what the x should be. So x is negative 1 works in both. X is negative 7 doesn't work in either of them. But as soon as it doesn't work in one, we reject it. Okay. So now that we have these, we can solve questions like this guy. Okay? So questions like this are, we cannot make the bases the same. We've already got a base of 3 on the left. We can't rewrite that anyway. And the base of 6 on the right cannot be written as a 3. So our only option is to use logs to solve. So what we're going to do is we're going to log both sides and then use log laws to solve. Okay. So I'm allowed to log both sides of an equation. I can't just log one side, but I can log both sides of an equation, similar to how you could square root both sides, or you could square both sides or divide both sides by 2. You can log both sides of your equation. So I'm going to do that. Okay. So I cannot make bases the same. So need to use logs. We will log both sides of the equation. and use log laws to isolate x. Okay. So this is my equation, right? If I log both sides, it literally is just that. We're going to log both sides. Now our log laws say that if we have an exponent, we're allowed to bring that exponent down outside in front of the log. So on the left-hand side, the entire x plus 1 is going to come down and multiply with the log, which now would just have a 3 inside. On the right side, we're going to bring the x down in front and multiply that with the log of 6. Okay. Now, one option is to divide both sides by log 3 or divide both sides by log 6 at this point. But on the left, the problem is that the log 3 is multiplying by both the x and the 1. So I'm actually going to distribute it into the brackets so that I have x log 3 plus 1 log 3. And on the right side, I still have x log 6. Now my job is to try and isolate x. And a reminder, log 3, log 6, these are just numbers. They're not nice numbers, but they're just numbers. So I want to try and get all the terms that have an x on one side of the equation. So I'm going to move the x log 3 over to the right-hand side. And I would do that by subtracting it the same way I would subtract a 5x or a 2x. Log 3 is just a number. Okay. Now that I have that on the right-hand side, I'm going to factor out an x. The left is still just log 3. Okay. Now on the right, I can rewrite the stuff in brackets using my quotient log law as log of 6 over 3. And log of 6 over 3 would be log 2. And now I can divide both sides by log 2 to get the x by itself. And we would be done. Okay, again, a reminder, log 3 over log 2 is not the same as log of 3 over 2. Okay, those are not equal. You have log 3 divided by log 2. That's the best you can do. You cannot simplify. Some questions will ask you to figure out what this is to the nearest decimal. You can plug that into your calculator as log 3 divided by log 2 and actually get a number answer, a decimal answer. This would be considered exact form. And most questions will ask you to leave it like this. Okay. So when you have an exponential equation where the bases can't be made the same, that's the toughest type of equation for you to solve because you need to use your log laws quite a bit and your knowledge of exponentials. So the first step is always log both sides, then bring those exponents down. If it was an exponential equation to begin with, you will always have that step. You will always need to bring the exponents down. Then likely you're going to have one or both sides where you need to do some sort of expansion, like we did right here. Okay. And then get all the terms with your x on one side and all the terms with no x on the other side and simplify from there. So we are going to try one more, and then that will be it for today. So again, you cannot do this. That is not a rule. That is mathematically incorrect. This is not allowed. The x to the negative 1 is not on the 3 and the 2. This is not equal. This would equal 6 to the x minus 1. But that's not what we have. We have no brackets around the 2 and the 3. The brackets are clearly telling us the x minus 1 is only on the 2. So we cannot apply that exponent to the 3 and the 2, all right? There is no way we can make these have the same bases because on the left-hand side already there are two separate bases. There's a 3 and there is a 2. So we cannot make the same bases. So our first step is log both sides. Okay. Now our second step would usually be bring the exponents down, which we can do on the right, but on the left, we don't have an exponent that is on this whole term, but we do have log laws that we can use. So we're going to use log laws here. We're going to use the multiplication one. And we're going to split this up into log of 3 plus log of 2 to the x minus 1. Now that we've done that, we can bring our exponents that we have down. We have an exponent on the left, the x minus 1, and we have an exponent on the right. The log 3 is just going to stay over here by himself. Oh, we're thinking again. Okay. So once we bring the x minus 1 down, we're just left with a log 2. And on the right, we're going to bring the 2x down because that's our entire exponent. And we've got log 6. So again, a reminder, log 3, log 2, log 6, these are just numbers, not nice numbers, but they're just numbers, okay? You can think of them like a 5, a 7, and a 10, or whatever, but with a lot of decimals and really gross. So the next thing we need to do, like we did in the previous question, this x minus 1 in brackets is being multiplied with the log 2. So I can distribute that log 2 in. And this becomes x log 2 minus log 2 equals 2x log 6. Now again, we want everything with an x on one side and everything without an x on the other side. So I need to move this x log 2 over to the right. And I'm going to leave the log 3 and the minus log 2 on the left. Now that we've done that, we've got a couple things we can do. On the left, we can simplify this back together using log laws, using the division log law. And on this side, we need to factor out an x. Okay. So on the left, we're going to have log, it's going to be 3 over 2 equals x times, we've got a 2 log 6 in the first term and a log 2 in the second term. Now on the left, you can rewrite this as 1.5 if you want, or you can leave it. On the right, we now need to simplify all the stuff in brackets using log laws. So we need to use power law to rewrite. That 2 log 6. So if you want to, you can write this as 1.5. I'm going to keep using 3 over 2. So the x is still here, but we need to rewrite this as log 6 squared minus log 2, or log 36 minus log 2. You can leave it as 6 squared for now if you like. Once we have that, we can use our log laws again, our division one. To simplify this further, we get log of 36 over 2, and 36 over 2 is 18. Now that we have that, we can divide both sides by log 18. So on the left, we've got log of 3 over 2 divided by log 18. And again, this would be an exact answer. You could also have log of 1.5 over log of 18. If it asked you for a decimal answer, you would plug this into your calculator and come up with an actual number. Okay. So you've got a couple things from today. The first is being able to solve an exponential equation where the bases are the same. Once the bases are the same, the exponents must be equal. The second was solving a logarithmic equation. If possible, rewrite it in exponential form and solve. If not, if you have the same bases and you have a logarithm on both sides of the equation, you have a single logarithm. If you have something like 10 back out, if you have log base a of x equals log base a of y, then x must equal y. Okay. If you have a to the power of x equals a to the power of y, then same thing, x must equal y. So if you have an exponential or a logarithmic equation where the bases are the same and there's only a single exponential or single logarithmic on either side, then you have this x equals y situation here. If you have an exponential where you cannot make the bases the same, you would log both sides, simplify if necessary, and bring the exponents down, and then you can use your log laws to solve for x. So there's a couple different types here. Make sure you try one or two at least of each type. Okay. Question 4 and 5 would probably be the most difficult ones. They require the most steps. There's lots of room for error in simple algebraic mistakes. So please do make sure you try some of these questions.